Let me begin with a word of prayer. So, Heavenly Father, we thank you for this morning, and thank you for these students, this class, and for your many blessings. Just ask that you to bless our work today, help us to glorify you. We do, Lord. In your name I pray, Lord Jesus. Amen. So, it's pretty exciting, the events of last night. You know, not often you see a president elected to a third term. So, that's right. I said it. Sorry. But anyway, it'll be interesting to see what happens over the next few weeks. Well, so we're studying, and so I, some of you guys asked me, will I give you the formula sheet that you'll be able to work off of in the next test? And I had said, oh, maybe I'll have it for you Wednesday. That was overly optimistic on my part, because my office is, well, you guys know what they do with the magic trick before they do the stuff with the cards? You know, they take those cards and they shuffle them. Well, that's kind of what's happened to my office in moving. So I remember seeing the formula sheet before I moved. I've seen it. It's in my office somewhere. I will find it. Or maybe I'll create a better sheet. The one that I have is basically an ancient scan from the textbook, and it's a little fuzzy. I could probably do better. So I'll try to get that to you sometime soon. But anyway, so we're talking about Laplace transforms. Really the Laplace transform technique, and up to this point, let me remind you what we've done. We've said that the Laplace transform of, let's say y, which is probably a function of t, of s is equal to the integral from 0 to infinity of e to the minus st times f of t dt. We also like to use the notation big F of s for this. So we have two competing notations for the Laplace transform. The one is this funny looking L of y to emphasize the transform aspect of it. The other one is this big F because it's just ever so much more fun to do algebra in the letter big F as opposed to the script L transforming curly bracket of y of t. So anyway, with that, we last time have calculated a number of basic Laplace transforms. So for instance, we calculated the Laplace transform of e to the at, and we found that that was 1 over s minus a. We found that the Laplace transform of cosine of bt was equal to s over s squared plus b squared. We found that the Laplace transform of sine of bt was b over s squared plus b squared. We found that the Laplace transform of e to the at times y of s was equal to the Laplace transform of y at s minus a, or if you like, f of s minus a here. If I'm using the notation, the Laplace transform of y is equal to f. Okay. This is a package deal. So this is called the shift theorem. The last one is called the shift theorem. And if you know the shift theorem, then you can use the shift theorem to get from these two basic formulas to the shifted versions, right? Now the shifted versions I just straight up derived last class, right? From just basic calculations. But if you use the shift theorem, here's how that goes. So we take this formula and we replace s with s minus a. So you get s minus a over s minus a squared. Now last class I had an alpha and a beta squared. Here it's, you could use a and b, you can use alpha and beta. I mean, you can use whatever letters you like, as long as you don't use like a t and an s. That would be bad. Because those are already being, those are playing a different role here already. So those are probably not the best choice. And then here, if I take my s and replace it by s minus a, I get b over s minus a squared plus b squared. All right, so these things we need to know about. Oops. Oh well, that marker is no more. I think that's all we got so far, right? So next on the agenda is to calculate. We also have that the Laplace transform is linear, right? So let me just take that out for a spin. For example, if I was to calculate the Laplace transform of 3e to the 7t minus 17 cosine of t, well, that would just be equal to 3 over s minus 7 minus 17 s over s squared plus 1. There you go. That's linearity. I'm just using Laplace transform on each thing, right? Let's do a harder one. Example 2. What if I was calculating, say, the Laplace transform of the sine of 3t plus 8? How would I do that? So I need to, first of all, use some trigonometry that we're all supposed to know, but you may or may not remember. So sine of 3t, I mean, you guys probably know this. Sine of 3t cosine of 8, right? Plus cosine of 3t sine of 8, right? This is the adding angles formula for sine. Lo and behold, now we've got stuff that's Laplace transformable, right? That actually has a technical meaning that I probably should define. Let's see here. I'll get to it. Oops, my bad. So we're done. This is, 3 cosine of 8 over s squared plus 9 plus, the sine of 8 times s divided by s squared plus 9. Do you guys follow? I hope. See if I actually brought my, a fresh roster. Maybe I should use that. Let's see here. Well, these are kind of old, but since I saw it, there you go. Give me a second here, guys. Like I said, I'm still struggling to find my notes for this class. They're in my stacks of stuff somewhere, and I remember most things in this class just off the top of my head, but this particular thing I want to make sure I don't mess up. Just give me a second here. What I'm trying to remember is the definition. Say f mapping, say, from 0 to infinity to the reals has exponential order alpha provided a certain conditions met. And I think, want me to go off memory, see if I guess right? There exists, m greater than 0 and alpha in the reals for which f of t absolute value is less than or equal to m e to the alpha t for t greater than 0. No, but don't take my word. I wouldn't write that down just yet. Give me a second here. Because, like I said, I need to check my notes. So we're currently in chapter, 7 of my notes, I believe. Chapter 6, my bad. So definition 6.29 on page 168 of my lecture notes. Function f of t is said to be exponential order alpha if and only if there exists a positive integer constant. Oh, that's not even spelled right. Yowzers. Okay, so I almost got it right. So there's another thing in play, and t greater than 0. There are two things, t greater than 0, for which that's the condition, but it's t greater than t. All right. I have to mention this in passing because the basic theorem that we have is this. So here's the theorem. And the theorem simply says this: if f is piecewise continuous on 0 to infinity, and has exponential order alpha, then the Laplace transform of f of s exists for s greater than alpha. So if you're worried about the underlying analysis here, like which functions can we, which functions can we take the Laplace transform of, this is the story. And I'm not going to belabor it too much. I'm just going to read you the deal. So like e to the at has exponential order a, sine t and cosine, sine bt and cosine bt, these both have exponential order 0. E to the at times sine cosine times sine bt or cosine bt, they've got exponential order a. And finally, t to the power n is exponential of order 1. Wait a minute, what? Oh, that's just an example. Never mind. Irrelevant. Okay, so all of this said, I almost never really test on this because it's kind of like just beside the point for this class. This is not where this class is operating at. If this was a major math class that was more of an analysis class, we would dwell here. All right, but that is not the case here. But I do need to mention it because that's basically the underlying analysis that you would want to look at if you cared more about the scope of the method. Long story short, the scope of the method is it covers all of the functions we've talked about in terms of like sine, cosine, exponential, and soon we'll see polynomials, and also piecewise continuous versions of those. Like if we were to, do an exponential for a little bit and then do a sine for a little bit and then do a cosine for a little bit and switch them on and off, this method would still cover that. But anyway, so let me erase that since we don't really, have much more to do with that. I just owe you a comment. So the comment has been made. I mean, in a given year, I may or may not even have a homework problem on this, all right? So let's see here. The next theorem we need to look at is to take the Laplace transform of the derivative. So how do derivatives transform? So let's calculate the Laplace transform of dy dt of s. All right, let's calculate it. All right, so here we go. We're going to look for the Laplace transform of dy dt of s. What would that be equal to? Would that be equal to the integral from 0 to infinity, right? And we have e to the minus st times dy dt. All right, dt. And technically, we should probably assume that like y here has exponential order alpha or something, but again, I'm not going to belabor those points. How do you do an integral like this? So let me remind you something. We know that the derivative with respect to time of y times e to the minus st, treating s as a constant here, is what? It is dy dt times e to the minus st, right? Minus sy e to the minus st. Why is that? What did I just do? Product rule. Right, this is the product rule. So if we use the product rule, we can solve for part of what we have here already, right? And we can notice, where is that? That's this term right here, right? So I can replace the red term with the difference of the derivative of y times e to the minus st plus sy e to the minus st, right? dt. Right? What happens when we integrate a total derivative? This piece here, what do we get? We get y e to the minus st, and we're going to evaluate from 0 to infinity. Don't tell the other math professors I use this notation, but it is terribly efficient. And your engineering professors probably use it, and that's fine. Because it is a shorthand for a limiting process, all right? It's a shorthand for a limiting process, truth be told. Now the other piece, I'm going to pull that s out, and we've got plus s times the integral from 0 to infinity of, well, y, I'll write the e to the minus st first, e to the minus st y dt, right? So can you recognize what is this? What is this here? What are you looking at there? What is that? There's really one definition you need to learn here, and that is the definition of the Laplace transform itself, right? That is the Laplace transform of y. All right, technically of s. Writing the of t on the y is optional, right? Anyway, so that's that. The other piece, well, let's work it out. We'd have something like, you know, y at infinity times e to the minus s times infinity, you know, and then minus y of 0 e to the 0. So technically that's plus s times this, right? The thing is, if y has exponential order alpha, then if we look at this more carefully, I guess I can. What would this be? This would be what? Really, it's the limit. I'll write out the limit this time. Limit as t goes to infinity, right, of y of t times e to the minus st. That's what we actually have there if I write out the details, right? So then minus y of 0 plus s times, I'm tired of writing that, so I'm going to write the big Y, if you don't mind. Big Y of s. That's our other notation for the Laplace transform, the big Y. But the thing is, with this term right here, right? What's the story there? If it has exponential order alpha, what is this? You know, what is, if we take the, you know, the absolute value of y of t e to the minus st, right? And that's going to be less than or equal to m e to the what? Goodness gracious. Alpha t, I think it was. And then times e to the minus st for t greater than that big T, you know? And that is equal to m e to the minus parentheses s minus alpha t, right? So if y has exponential order alpha, that term does what? As t goes to infinity, right? You're past the big T, so the bound is in play. This goes to what? That goes to 0 for s greater than alpha, right? So for s greater than alpha, as t goes to infinity, that goes to 0. Which leaves us with the following result. The Laplace transform of dy dt, right, at time s, it's equal to s times the Laplace transform of y of s, all right, minus y of 0. Sometimes we don't like that notation. This notation is kind of clumsy. This is equivalent to saying the Laplace transform of y prime is equal to s times big Y minus y of 0. All right, so that's a slightly more condensed version of the same theorem. You guys with me? So that's very interesting, actually, because what it's just showing us is that when we transform from the time domain to the so-called frequency domain, S is called the frequency domain, what's going on is we're changing a derivative in t to a multiplication in S. That's very interesting, because that means that as we take the Laplace transform, we're going to be able to trade a differential equation for an algebraic equation. How do we solve algebraic equations? With what? The answer, algebra, right? So we can do algebra. We should learn how to do algebra. We should remember how to do the algebra we knew how to do before when we were in high school or earlier stuff. I don't know. There are various states of decay in algebra here. I believe in my heart at some point everyone in here knew how to do the algebra you've forgotten. But you need to remember. Or maybe you didn't have good teachers, you were cheated, as Dr. Sprano likes to talk about. In which case, well, I hope I'm giving you enough practice this semester that by the time you leave this course, you will be masters of algebra. Because this course is certainly much more about algebra than it is calculus. Although I'm sure that the calculus that I bring up is also sometimes new. All right, so let's see here. What if we had two derivatives? What would happen then? What if we were to take the Laplace transform of d squared y, dt squared? What would that be? Well, we would be talking about the Laplace transform of d dt, right, of dy dt. Yeah? That's what that is. So we can use what we just calculated to do this one, right? What would this be? This would be equal to s times the Laplace transform of dy dt of s minus what? Minus dy dt of 0. Right? I'm just applying the previous theorem with y set to dy dt. Do you guys follow? I hope. But the thing is, we also know what this is, right? So we've got s times the Laplace transform of y minus y of 0 minus, well, I'm going to say y prime of 0 because I'm tired of writing dy dt, if you guys don't mind, from that. So let's clean it up. What we have just derived is the following result. The Laplace transform of y prime prime is equal to s squared times the Laplace transform of y of s minus, check this out, s times y of 0 minus y prime of 0. What would happen if we were to calculate the Laplace transform of y prime prime prime, do you think? Well, let's work it out. Yeah? So the Laplace transform of jerk y prime 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 would be equal to the Laplace transform of y prime prime times s minus y prime prime of 0. But we know what that is. This is s times s squared Laplace transform of y minus s y of 0 minus y prime of 0. So therefore, we find the Laplace transform of the third derivative is simply equal to s cubed times big Y minus s squared, see, s times s squared y of 0 minus s times y prime of 0 minus y prime prime of 0. There you go. That's how the Laplace transform of the third derivative transforms. Are we good? We can obviously generalize this pattern to the nth derivative, but I'm not going to bother at the moment because, well, you guys should have to do something. Let's see here. So you figure it out. So what is still left for us to do in terms of basic function stuff is to figure out the Laplace transform of t. So let's go back and do that. What's the Laplace transform of t? So let me say it this way. What about polynomials? Is really my question. So we'll start with, well, we already know the Laplace transform of 1 is what? 1 over s, right? We got that one last. That one was easy. What is the Laplace transform of t? Well, I guess we'll just try to calculate it, right? We've got integral from 0 to infinity of what? E to the minus st times t dt. How do we do that integral? I feel like this is integration by parts. Yeah. So let's see here. I feel like I'm going to write the t first for my purposes. If I do that, I think I'll make this my dv, and I'm going to make this the u, right? So I've got t times minus 1 over s e to the minus st that's uv minus the integral from 0 to infinity of, let's see here, minus 1 over s e to the minus st times du, which is dt. And of course, this isn't quite right yet either, because what do you have to do when you have integration by parts of bounds? What do you have to do with the uv term? You have to feed it to the bounds just like the other thing, right? So I'm missing a evaluation from 0 to infinity here. Don't forget that. And so great. What I have then is, well, I'm going to write out the limit, because if I don't write the limit, it bothers me. Limit as t goes to infinity. The upper bound ends up giving me a minus t e to the minus st over s. All right, and then I've got plus 1 over s times t e to the minus st. I'm just writing this out symbolically and emphasizing we're plugging t equals to 0 into that, right? So what is that? I still have the integral term past that, you know. This one, when I integrate this, what do I get? I get, I think I get minus 1 over s squared e to the minus st evaluated from 0 to infinity. So you guys tell me, what happens to these first two terms? Anything? Yeah, I think they're both 0. So this one's 0 because for s positive, you've got a t times an exponential with a negative argument. Exponential growth wins. It's going to kill the time. If we did like Laplace Transform, listen to me, L'Hopital's rule, that one. This one's just straight 0. You plug 0 in 0, right? So either by L'Hopital's rule or by direct evaluation, all this stuff is 0. That, on the other hand, maybe gives us something. So what have we got? We've got, you know, limit as t goes to infinity of like minus, oh, minus and minus is a plus, right? No, wait a minute, there's only one minus, my bad. E to the minus st over s squared, right? Plus 1 over s squared e to the 0. Again, that goes to 0 because it's just an exponential. So this goes to 0 as well, all right? And let me emphasize that all three of these things, all three of these conclusions I just made, well, not this one so much, but this one and this one rest on the assumption s is greater than 0. I'm assuming s is greater than 0 in order to draw the conclusion that those terms limit to 0. So what am I left with? 1 over s squared. Right. So what I find then is the Laplace transform of t is simply equal to 1 over s squared. Yeah.
So is that like another pattern, like the Laplace transform of t squared would be 1 over this cube?
That's a question. What happens when we take, what's the Laplace transform of 1 over t squared? Not 1 over t squared. Yeah. Maybe. I don't know right offhand. I don't think it's just that. I think we end up, something else enters the story here. So let's try that out. What would the Laplace transform of t squared be? Maybe. Maybe I can find a way around it. I feel like there's a trick here I can exploit. I have f of s. Let's say big Y. I got big Y, which is a function of s, right? Is equal to the integral from 0 to infinity of e to the minus st. Well, let's say times t to the n. Let's calculate the Laplace transform of t to the power n. Let me see if I can. Let me see if I can do some kind of Jedi mind tricks here to just avoid the calculation. But yes, of course, we could integrate by parts n times, take our medicine, do it in the straightforward way. But let's try to cheat. So I'd like to know what the Laplace transform is of t to the n, right? How? No, that won't work. Rats. I know there's a way to cheat around this thing. I forgot what it is, though. How is... I mean, we know the Laplace transform of 1 is 1 over s, right? And that's also equal to the integral from 0 to infinity, like e to the minus st dt, right? Yeah? Let me suggest something a little bit outside the box. Take the partial derivative with respect to s. What happens? Take the partial derivative with respect to s of that relation. Let's see here. So, partial derivative with respect to s of both sides. So we've got partial s, 1 over s is equal to, and now I'm going to, this is the Jedi mind trick part of it, if you believe in that sort of thing. Anyway, it's just unjustified advanced calculus that I won't even justify in advanced calculus, truth be told. But it can be done nonetheless. This is Richard Feynman, the great 20th century physicist's favorite trick, one of them, which is that you can, change the order. I bring the derivative inside the integral. The integral's over t, the derivatives over s. They're independent variables, so you should be able to commute them, right? Great. So this is minus 1 over s squared. What happens here? What's the partial derivative of that? That's what? Integral from 0 to infinity of minus t e to the minus st. Right? Therefore what? 1 over s squared is the integral from 0 to infinity of t e to the minus st, which is what we just did what? We just derived that by all of this. To which you should be like, well, if you know this, why didn't you just partial differentiate this with respect to s and save us this mess? We have no love of calculus 2. Don't bring it back to us, right? So if you appreciate this, what can we do? Now that we have the boxed equation, what can I do? If you believe this, if you believe in magic, I mean, I hope you do. So we can calculate partial s of 1 over s squared, and that will be partial s of the integral from 0 to infinity of t e to the minus st. But what happens when you take that partial derivative inside? You get what? So on the one side, we get over here, we get what? We get minus 2 over s cubed. And the other side, we get integral from 0 to infinity of what? Minus t squared e to the minus st. Notice that the t just slides past the partial s, right? They're independent variables. You get a minus on both sides, what do we got? We've got 2 over s cubed is equal to the integral from 0 to infinity of t squared e to the minus st dt. But what is that? Well, that is the Laplace transform of t squared, my friends. That is the Laplace transform of t squared. You're almost right, but what are we missing? You almost got it, but what happens? What happens when we differentiate again? If we differentiate again, we get a 3 times 2 over s to the 4th is equal to the Laplace transform of t cubed of s. I'm just going ahead and canceling the minuses that come from both sides of differentiation. And so generally speaking, the Laplace transform of t to the power n of s is equal to what? Apparently n factorial divided by s to the power n plus 1. Hooray! So there you go. That's the Laplace transform of t to the n. And I narrowly avoided the problem of doing integration by parts n-fold times, right? This trick of differentiating an integral with respect to a parameter which you're not integrating is an important trick of advanced calculus, or just generally calculus we don't teach you in the calculus sequence. It's actually really important to engineering and physics calculation for doing integrals that maybe you haven't seen. Like if you study quantum field theory, this kind of chicanery is really, really important to understanding how to generate new formulas from old. Listen, so now that we have this, we can use linearity to calculate the Laplace transform of the polynomial. The polynomial looks like what? A sub n t to the n plus dot 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 plus, say, a2t squared plus a1t plus a naught. Hey, we can write down the formula for this now, right? It's what? It's a sub n times n factorial over s to the n plus 1 plus a sub, well, plus dot 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 dot. Eventually we get to a sub 2 times 2 over s cubed plus a sub 1 over s squared. Finally, plus the thing we could have done last class, a sub naught over s. And there is the Laplace transform of an arbitrary polynomial. So at this point, well, you can ask other questions that are a little bit more subtle. What happens when n is not a counting number? What if n is not an integer, a positive integer? What is the Laplace transform of t to the n in that context? You know?
Are you speaking in the complex sense? Or just...
Oh, no. N is, like, what if n is like 1.5?
okay.
Like, what's the Laplace transform of the square root of t, for instance? Is that something you can do? Right. So that's something we should circle back to another day, but I'll tell you the answer sort of roughly at the moment. It involves something called the gamma function, but I don't want to rush through that without having about 10 minutes to talk about what is this gamma function. The gamma function is some sort of continuous extension to the factorial. So like if you want to understand like what is 1.3 factorial, the gamma function kind of answers that, but not directly. Anyway, so there's that. But other than that, I think that pretty much covers it for in terms of like what's the Laplace transform of our basic functions. This is it. You can also do stuff like take the Laplace transform of the power series. Right? If you have a power series representation for your function, how would you find the Laplace transform? I think this kind of lays the groundwork for that, doesn't it? You could take the Laplace transform of a series expansion for a function, like its Maclaurin expansion, and it would replace you would then obtain a corresponding, well, apparently Laurent series in the frequency domain, which is probably part of the reason that complex analysis plays a large role in deeper applications of Laplace transforms. Because once you talk about infinite series of like inverse powers, you probably need complex analysis to fully understand that. But the other thing I will say is the other large chunk missing for us right now is how you take the Laplace transform of a discontinuous function. Like part of the whole beauty of this method is that it treats the discontinuous case. So we need to get to that. But before I get to that, I first need to tell you something like next class we're going to talk about the inverse Laplace transform, how to calculate that. And then after that, once we've done that groundwork, we'll get back to the discontinuous case. So thanks, guys.